Welcome to the fourth lecture in Electrical Engineering Fundamentals. In this lecture, we will define some additional terms to facilitate circuit analysis. We will also learn about a powerful technique of circuit analysis, which is the node voltage method. We will illustrate this technique by solving several examples and problems with independent and dependent sources, as well as some special cases. So far we have analyzed simple resistive circuits by applying Ohm's law and Kirchhoff's laws. Though we can use this approach for all circuits, it becomes more tiresome in complicated circuits. In this lecture and the following lecture, we will learn two powerful techniques of circuit analysis, namely the node voltage method and the mesh current method. These techniques provide direct approach of describing complicated circuits with minimum number of simultaneous equations. To discuss the more involved methods of circuit analysis, we must first define basic terms necessary for a clear description of circuit features. These terms include the following. The node, which is a point where two or more circuit elements connect. An essential node, which is a node where three or more circuit elements connect. A path, which is a trace of adjoining basic elements with no element included more than once. A branch, which is a path that connects two nodes. An essential branch, which is a path that connects two essential nodes without passing through an essential node. A loop, which is a path whose last node is the same as the starting node. And finally, the mesh, which is a loop that does not enclose any other loop. We will illustrate each of the previous terms using this figure. On this figure, we can identify 7 nodes, which are points where two or more circuit elements connect. These nodes are node A, node B, node C, node D, node E, node F, and node G. An essential node is a point where three or more circuit elements connect. From the 7 nodes previously identified, we can find 4 essential nodes. These nodes are node C, node B, node E, and node G. A branch is a path that connects two nodes. We can identify 10 branches in this circuit. These branches are V1, R1, R5, R3, R2, V2, R4, R6, R7, and I. An essential branch is a path that connects two essential nodes without passing through an essential node. In this circuit, we can identify 7 essential branches. These essential branches are V1 and R1, R5, R3 and R2, V2 and R4, R6, R7, and I. A mesh is a loop that does not enclose any other loops. In this figure, we have 4 meshes. The first mesh consists of V1, R1, R5, R3, and R2. The second mesh consists of V2, R2, R3, R6, and R4. The third mesh consists of R6, R5, and R7, and the final mesh consists of R7 and I. In this part of the lecture, we will learn about one of the most powerful techniques in circuit analysis, which is the node voltage method. The steps required to apply the node voltage method are the following. Mark clearly the essential nodes on the circuit diagram. N equals to the number of essential nodes. Select one of the essential nodes as the reference node. This is usually the node with most branches. Define the node voltages on the circuit diagram. The node voltage is the voltage drop from the essential node to the reference node. Generate the node voltage equations by writing the currents leaving each branch connected to a non-reference node as a function of the node voltage, summing these currents to 0 according to Kirchhoff's current law, where the number of KCL equations equals to n minus 1. The node voltage method will be clarified when we solve a couple of examples and problems. In example 1, we need to use the node voltage method to find V1 and V2. We start our solution by identifying the essential nodes on the circuit, which are node 1, node 2, and node 3. The reference node is chosen to be node 3, which is the node with the most number of branches. Node voltages at node 1 and 2 are defined as V1 and V2 with respect to the reference node. By applying KCL at nodes 1 and 2, we get applying KCL at node 1 yields I1 plus I2 plus I3 equals to 0, which can be written as V1 minus 10 over R1 plus V1 over R5 plus V1 minus V2 over R2 equals to 0. Applying KCL at node 2 yields I4 plus I5 minus 2 equals to 0, which can be written as V2 minus V1 over R2 plus V2 over R4 minus 2 equals to 0. We have two equations with two unknowns. Solving equations 1 and 2, we get V1 equals to 9.09 volts and V2 equals to 10.91 volts. In example 2, we need to use the node voltage method to find branch currents IA, IB, and IC. We also need to find the power associated with each source and determine whether it's being delivered or absorbed. We start our solution by noting that the circuit has two essential nodes, node 1 and node 2. We choose the reference node to be node 2, and we define the voltage at node 1 as V1 with respect to the reference node. By applying KCL at node 1, we obtain V1 minus 50 over R1 plus V1 over R2 plus V1 over R3 minus 3 equals to 0, which yields V1 equals to 40 volts, from which IA equals to 50 minus V1 over R1 equals to 2 amps, IB equals to V1 over R2 equals to 4 amps, and IC equals to V1 over R3 equals to 1 amp. The current IA is flowing in the direction of the voltage rise across the terminals of the voltage source. Hence, the power equation is written as P equals to minus V times IA equals to minus 100 watts. Since the power is negative, it means that it's being delivered or generated, so the delivered power equals to 100 watts. The current in the current source is flowing in the direction of the voltage rise across its terminals, from which the power equation is written as P equals to minus V1 times I, which equals to minus 120 watts. The power here is also negative, which means that it's being generated or delivered. The delivered power equals to 120 watts. The same previous approach of the node voltage method applies on circuits with dependent sources. However, here we need to add the constraint equations of dependent sources to the node voltage equations. In example 3, we need to use the node voltage method to find the power dissipated in R3. We start our solution by noting that the circuit has 3 essential nodes, node 1, node 2, and node 3, and choosing node 3 as the reference node. Node voltages at node 1 and 2 are defined as V1 and V2 with respect to the reference node. By applying KCL at node 1, we get V1 minus 20 over R1 plus V1 over R2 plus V1 minus V2 over R3 equals to 0. This is the first equation. Applying KCL at node 2, we get V2 minus V1 over R3 plus V2 over R4 plus V2 minus 8 IY over R5 equals to 0. This is the second equation. However, we have two equations with 3 unknowns, V1, V2, and IY. The third equation can be derived from the dependent source, where Ry equals to V1 minus V2 over R3. Now we have 3 equations for 3 unknowns. Solving these equations yields V1 equals to 16 volts, V2 equals to 10 volts, and IY equals to 1.2 amps. The power dissipated in R3 is given by P equals to IY squared times R3 equals to 7.2 watts. In the node voltage method, we have 2 special cases. The first one is when a voltage source is the only element between two essential nodes. One of them is the reference node. In this case, the node voltage method is simplified since one of the node voltages is restricted by the voltage source. The second case is when a voltage source is the only element between two essential nodes. None of them is the reference node. In this case, the two nodes are considered as one supernode. The currents flowing out of both nodes are written in one equation. These two cases will be further clarified by the following examples and problems. In example 4, we need to find V2 using the node voltage method. We start our solution by noting that this circuit has three essential nodes, node 1, node 2, and node 3, and choosing node 3 as the reference node. The voltages at nodes 1 and 2 are defined as V1 and V2 with respect to the reference node. The 100 voltage source is the only element between essential node 1 and the reference node. This is the first case mentioned in the previous slide, from which V1 is restricted to be equal to 100 volts. Since V1 is known, we will need only one equation to find V2. Applying KCL at node 2, we get V2 minus V1 over R2 plus V2 over R3 minus 5 equals to 0, from which V2 equals to 125 volts. In example 5, we need to find V2, V3, and Ix using the node voltage method. We start our solution by noting that this circuit has four essential nodes, node 1, node 2, node 3, and node 4, and choosing node 4 as the reference node. The voltages at nodes 1, 2, and 3 are defined as V1, V2, and V3 with respect to the reference node. The 50 volt source is the only element between essential node 1 and the reference node, hence V1 is restricted to be equal to 50 volts. The dependent voltage source is the only element between essential node 2 and essential node 3, so we can form a supernode from node 2 and 3. Applying KCL at the supernode nodes 2 and 3, we get V2 minus V1 over R2 plus V2 over R3 plus V3 over R4 minus 4 equals to 0. Applying KVL at the supernode loop yields minus V2 minus 10Ix plus V3 equals to 0. The dependent source constraint is Ix equals to V2 minus V1 over R2. Solving these three equations for the three unknowns V2, V3, and Ix, we get V2 equals to 60 volts, V3 equals to 80 volts, and Ix equals to 2 amps. In problem 1, we need to use the node voltage method to find V1, V2, and I1. We also need to find the power delivered by the 12 and 5 amp sources. We start our solution by identifying the essential nodes in the circuit, which are node 1, node 2, and node 3, which is chosen as the reference node. The node voltages at nodes 1 and 2 are defined as V1, V2 with respect to the reference node. By applying KCL at node 1, we get 5 plus V1 over R1 plus V1 minus V2 over R2 equals to 0. Applying KCL at node 2 yields V2 minus V1 over R2 plus V2 over R3 plus V2 over R4 minus 12 equals to 0. Solving equations 1 and 2 for V1 and V2, we get V1 equals to 48 volts and V2 equals to 64 volts, from which I1 equals to V1 minus V2 over R2 equals to minus 8 amps. IY is flowing in the direction of the voltage rise across its terminals, from which the power equation is written as P equals to minus V2 times IY equals to minus 768 watts. Since the power is negative, it means that it's being generated or delivered. The delivered power equals to 768 watts. For Ix, the current is flowing in the direction of the voltage drop across the terminals, from which the power equation is written as P equals to V1 Ix equals to 240 watts. Since the power is positive, it means that it's being absorbed or dissipated, from which the delivered power equals to minus 240 watts. In problem 2, we need to use the node voltage method to find the voltage V. We start our solution by noting that this circuit has three essential nodes, node 1, node 2, and node 3, which is defined as the reference node. Node voltages 1 and 2 are defined as V1 and V2 with respect to the reference node. By applying KCL at node 1, we get V1 over R1 plus V1 minus V2 over R2 plus R3 equals to 4.5 amps. Applying KCL at node 2 yields V2 minus V1 over R2 plus R3 plus V2 over R4 plus V2 minus 30 over R5 equals to 0. Solving equations 1 and 2, we get V1 equals to 6 volts and V2 equals to 18 volts, from which I equals to V2 minus V1 over R2 plus R3 equals to 1.5 amps, and V equals to I times R2 plus V1 equals to 15 volts. In problem 3, we need to use the node voltage method to find the power associated with each source and determine whether the power is being delivered or absorbed. We start the solution by noting that the circuit has three essential nodes, node 1, node 2, and node 3, which is chosen as the reference node. The node voltages at node 1 and 2 are defined with respect to the reference node as V1 and V2. Applying KCL at node 1 yields V1 over R1 plus V1 minus V2 over R2 plus 6 I2 equals to 1.5 amps. Applying KCL at node 2, we get V2 minus V1 over R2 plus V2 over R3 plus V2 minus 80 over R4 minus 6 I2 equals to 0. We have two equations with three unknowns, V1, V2, and I2. The third equation comes from the dependent source constraint, where I2 equals to 80 minus V2 over R4. Solving these three equations yields V1 equals to 10 volts, V2 equals to 60 volts, and I2 equals to 4 amps. The power equation of the 1.45 amp source is given by P equals to minus V1I equals to minus 15 watts. Since the power is negative, it is delivered. The power of the 80 volt source is given by P equals to minus VI2 equals minus 320 volts, 20 watts. Since it's less than 0, it's also being delivered. And finally, the power of the dependent source is given by P equals to minus 6 I2 times V2 minus V1 equals to minus 1200 watts. Since the power is negative, it means that it's being delivered. In problem 4, we need to find V2 using the node voltage method. We start our solution by noting that the circuit has four essential nodes: node 1, node 2, node 3, and node 4, which is chosen as the reference node. The node voltages at nodes 1, 2, and 3 are defined as V1, V2, and V3 with respect to the reference node. Applying KCL at node 1, we get V1 over R1 plus V1 minus V2 over R2 minus 4.8 equals to 0. Applying KCL at the supernode, nodes 2 and 3, we get V2 minus V1 over R2 plus V2 over R3 plus V3 over R4 plus V3 minus 12 over R5 equals to 0. Applying KVL at the supernode loop yields minus V2 minus Ix plus V3 equals to 0. And finally, the constraint of the dependent source is given by Ix equals to V1 over R1. Solving these four equations for the four unknowns yields V1 equals to 15 volts, V2 equals to 8 volts, V3 equals to 10 volts, and Ix equals to 2 amps. In this problem, we need to use the node voltage method to find V2. We start our solution by noting that this circuit has four essential nodes: node 1, node 2, node 3, and node 4, which is chosen as the reference node. Node voltages at nodes 1, 2, and 3 are defined as V1, V2, and V3 with respect to the reference node. We notice that the 150 voltage source is the only element between essential node 1 and the reference node, from which V1 is restricted to be equal to 150 volts. Applying KCL at node 2, we get V2 minus V1 over R1 plus V2 over R2 plus V2 minus V3 over R3 equals to 0. And we have two equations related to the dependent voltage source. V1 minus V3 equals to 15 IY, and IY equals to V1 minus V2 over R1. Solving these three equations yields V2 equals to 120 volts, V3 equals to 132 volts, and IY equals to 1.2 amps. In problem 6, we need to find V2 using the node voltage method. We start by noting that this circuit has three essential nodes: node 1, node 2, node 3, and node 4, which is chosen as the reference node. The node voltages are defined with respect to the reference node as V1, V2, and V3. We also notice that the 10-volt voltage source is the only element between essential node 1 and the reference node, from which V1 is restricted to be equal to 10 volts. Applying KCL at node 2, we get V2 minus V1 over R1 plus V2 over R2 plus V2 minus 20 IX over R3 equals to 0. Applying KCL at node 1 yields minus Ix plus V1 minus V2 over R1 plus V1 minus 20 Ix over R4 equals to 0. Solving these two equations, we get V2 equals to 24 volts and Ix equals to minus 3.2 amps. If you have any questions, please don't hesitate and email me. Thank you.